The River Thames, along whose banks the fictional detective, Sherlock Holmes, tracked down criminals with the forensic science he'd invented.
Elementary, my dear Watson.
In his day, it was observation and deductive reasoning. It's all very different today. Now it's the comparison microscope. Polymerase chain reaction that causes a minute DNA sample to clone itself. Blood splatter analysis, which can show how many blows a murderer struck. And of course, DNA itself, with its national database of samples from nearly 1 million criminals. The tools of detection are now pure 21st century, in the age-old quest of detectives everywhere, to unravel the truth beyond reasonable doubt.
535 Foxtrot 3 TA received.
In a suburb of Birmingham, central England, PC Alison Geddes has been called out to investigate a burglary.
This wasn't discovered.
This burglary couldn't be more mundane, yet all the detective work of the new scientific methods
the key was
were
in
brought
that
to bear.
door.
Right.
PC
So
Geddes
I reckon
secures
they
the
must
area
have
against
broken
contamination.
Have you touched these pieces of glass, sir, at all?
No.
Right, that's fine. Just to double check. Yeah, that's looking like the favourite spot, I think.
Then she calls in the
Taking the pane of
specialist.
glass right out. OK, I'll get onto the radio and ask for our scenes of crime to attend. Yeah, I'm at the scene of this burglary. I wonder if you could ask Sokol to attend, please.
Even at routine domestic burglaries, scene of crime officers attend. Why so much effort?
Morning.
Hi, John, you all right?
Not too bad, thank you.
Because the same criminals commit other crimes, sometimes
sure.
much more serious
Okay.
offences. And if forensic evidence has caught a criminal once, he's on the database for life.
Was the key left in the door, do you know?
On the inside.
Yeah.
No matter how careful the burglars were, they will have left something of themselves behind. John still checks for fingerprints, but he's also looking for other, more telling, forensic clues. 10 years ago, this would just be broken
Yeah, it's
glass.
just roughly 3
But
fingers.
all
just-
glass is manufactured in a slightly different way. Carefully examined, fragments of glass powder, which may now be on the burglar's clothes, are as individual as fingerprints. Minute fibre traces left on the broken window can be just as damning. They too can be matched.
Okay, it's just one length of a dark coloured fibre.
Tango 49 receiving NG.
There are over 50 separate police forces in the United Kingdom, based around individual cities and counties. But they send all their forensic evidence for analysis to only 10 central laboratories.
Hi. She's got some evidence for you.
They process 100,000 evidence samples a year for police investigations. Edinburgh, Scotland. The whole of southeast Scotland is policed by Lothian and Borders Police.
Good afternoon, Forensic Science Lab.
For the first time ever, cameras have been allowed access to their forensic science labs to observe some of the new techniques used to solve crime. Expensive science that used to be reserved for high-profile crimes, like rapes and murders, is now a conveyor belt process for virtually every infringement. Take the glass refractive index microscope. Glass powder, too fine to be visible, found on a perpetrator's clothing and matched to shards at the crime scene can trap a criminal. The science is based on the simple schoolboy trick of bending light through water.
When you put a pencil in water, it appears to bend, and that's because the refractive index of water is different from the refractive index of air. So this is bending of light, if you like. When things are in media that's the same refractive index, then you don't see any change in the light pattern. So if you put diamonds in ice or water, you can't see them. It's a great way of smuggling them.
But when applied to today's technology, glass can be identified to the day of manufacture.
take these very tiny fragments of glass, put them in an oil. The microscope stage is heated. The refractive index of the oil changes as it heats up. So clearly at one point the glass will have the same refractive index as the oil, and at that point the glass disappears. The computer sees that, notes the temperature, and hence the refractive index, which is accurate to about 3 decimal places.
Breaking down other samples into their constituent elements can provide a characteristic profile, a scientific fingerprint. Gas chromatography is used on charred fragments from a fire to identify accelerants like gasoline or kerosene that were used to start that fire. The gas volatiles are extracted and the proportions of different hydrocarbons are measured. How much propane, butane, octane, all things that cause fires to burn faster. These Scottish scientists can even identify the region gasoline was bought from, down to an individual oil company or refinery. And liquid chromatography is used in the drugs lab. They can trace a batch of drugs to a particular dealer by how pure it is, what it's been cut with, even what sort of soil it was grown in. The human hair provides even more clues. One strand will reveal the recent history of a person's substance abuse. Drugs, alcohol, nicotine, everything taken for the past 6 weeks or more.
People always view hair as a dead tissue, but in fact you've got to remember that it's been made from a live tissue, and that is you. The drug is integrated into the hair structure, and as the hair grows it's pushed more towards the end. What we can now do is to analyse the hair for the presence of those drugs. So if you imagine the hair as being an extended record of you and what you've been sticking into yourself, we grow roughly 2 millimetres every week. And we've therefore got a time scale for the length of a hair, and it's also semi-quantitative as well, which means we know roughly how much drug.
This is the comparison microscope, which solved the case of the Belgian motorcyclist. In late spring of this year, a Belgian motorcyclist was driving down a major road just south of Edinburgh. As she began to slow down, a lorry driver ran into the back of her. She was killed, but the lorry driver drove off and later denied being anywhere near the scene.
The lorry driver initially denied having had any contact with the vehicle. Now the lorry was a powder blue colour, and in actual fact we found this powder blue colour on the rear tyre of the motorbike and also on the registration plate.
The lorry driver's lie was exposed when the 2 paint samples were put under the comparison microscope.
In effect, there's 2 microscopes plugged together at the viewfinder. And if we take the layers of paint, you're actually looking to see if they both came from the same vehicle. There'll be several layers of paint. So if you imagine them as my fingers there, what we do is we take those layers of paint, turn them round flat, put them on a microscope slide, and now we can see by looking at the comparison microscope with one sample on one side and one sample on the other that the 2 types of paint were exactly the same. Now that doesn't mean that it could only have come from that lorry, but the question must arise, where else did it come from on that road that day? So this is very good evidence that in fact the lorry had collided with the rear of the motorcycle.
Hi Sandra, what are you up to?
Searching for some semen.
This is Derek Scrimger. He analyses blood stains, how blood sprays out at a crime scene. He reconstructed the horrific sequence of events in the case of this murder. During a robbery, this man was hacked to death with an ornamental axe. Derek was able to show that the victim was attacked 3 times, in the hallway, in the living room, and then in the bedroom, before succumbing to an axe blow to the head.
Quite often in court cases we're asked, would the complainer be able to defend themselves? And in that sort of instance we're looking to try and identify whether the complainer was upright or lying on the ground at the time when more blows were being rained on maybe their head.
In this drugs-related murder, the victim bled to death after barricading himself in the toilet. But blood splash analysis revealed that he'd been repeatedly stabbed whilst in another room.
The larger blood stains are very often not the most important, it's the very fine ones. We're talking about spots of a millimetre or less. We can grade the spots by size, small or minute, the minute ones being indicative of proximity to impact.
When blood sprays onto a surface, it's possible to identify the angle at which it hit.
In this instance here we have blood which is flown directly onto a surface which gives us a circular pattern. As the angle of incidence decreases, we can see that the blood, not only has it moved down from the original stain, but there are tails starting to appear at the bottom of this, which implies that the blood has not come straight on, it's actually started to arrive at an angle. This blood has arrived on this surface, again not at 90 degrees, but at a very sharp angle, 10 degrees in fact, and has hit this surface and rolled down, giving a tail whereby the volume of blood is reducing as it goes down. We can do calculations to find out the exact angle of incidence, and from that you can work out where the body was when it was being beaten.
Sometimes bloodstains on the walls of a crime scene need a little more imaginative interpretation.
I was at a murder scene about 2 years ago, and the weapon was unknown at the time, and the pattern on the wall was the standard linear pattern, but there was 2 tracks, a double track, and it took a wee while for me to click that this was actually a claw hammer, and that the tracks were coming off the end of the claw when it was being rained down. That was quite useful to the investigating officers when they were looking for a particular weapon.
As a result of Derrick's evidence, a Guildford man was found guilty of murdering his wife. Of all the advances in forensic science over the last 5 years, DNA testing has had the most revolutionary effect. Central London. The head offices of the Forensic Science Service. Every week they test thousands of crime scene samples for DNA.
First thing we have to do is to remove the DNA from, say, a bloodstain. And that's done with a series of chemical processes. A very small amount of material is taken out of the stain. The amount of DNA we need for a test these days is incredibly small. We only need about 1/1,000,000th of a gram, ideally. So if there was a bloodstain on my shirt that you could see with your eyes or even a microscope, that would certainly be sufficient to test. The test we're researching now, and that we see coming available within the next year or two, would be dealing with the amount of DNA perhaps that I left just by touching a surface, the desk, a telephone, computer keyboard.
You would get the letter bomber, who would be very careful. They'd use rubber gloves to construct their bomb, write their letter, they'd cut all the letters out of the newspaper. They'd go to all of this problem, then they'd lick the stamp. And of course therein lies their DNA.
Here they're obtaining DNA where a suspect had drunk from a vodka bottle. That's enough to identify him. The reason so little DNA material is needed is because of PCR, a new breakthrough technique which makes the DNA clone itself, just like in Jurassic Park.
We take the DNA itself and chemically ask it to copy itself, so that we could take one copy of DNA, for instance, and produce 1,000,000 copies of the same. That's called polymerase chain reaction, or PCR. That reaction takes a couple of hours.
The DNA in this larger sample is then tagged with a colour, so it can be read by a laser.
Very simply, DNA fragments flow past the laser. The laser sees the colours. They'd appear as a series of peaks, which a computer can interpret.
Okay, I'm going to take a scraping from the inside lining of your cheek. Just open your mouth a little bit.
DNA from the scene of a crime can be compared with DNA taken in a small mouth swab from someone suspected of committing the crime. British police take 8,000 mouth scrapes for DNA testing every week.
The legislation allows the police to take a sample from anyone that's arrested for a recordable offence, that is, an offence which could potentially carry a criminal record. The police can use that power and obtain a mouth swab from you. That mouth swab can be analysed and compared to the database.
and DNA profiles are searched for matches using a simple computer software program.
If the numerical string we obtain, for instance, between your profile and the scene of the crime is different, then you could not be the source of the DNA at the crime. And it's important to realise that DNA tests eliminate a large number of innocent people very quickly.
PCR made it viable to set up a national database.
The UK had legislation to introduce a national database very early on, and that was matched by a very newly emerging technology, which meant that the UK had the world's first national database by a period of some 3 years. Most countries in the world are looking at DNA databases of some sort, basically modelled on what we've done.
Birmingham, central England, Britain's second biggest city. Here in a secret location, over 700,000 swabs of DNA are stored in 50 freezers for the database. Every day, 8,000 DNA samples arrive here by courier from all over the country. These are the swabs from every person in the country charged with a jailable offence. Their profiles are barcoded, batched, and loaded into the database. The DNA itself is then stored here.
If you are convicted of an offence, your record will stay on the database throughout your life. If the case is not continued with, or you're found not guilty, either by a court initially or by the appeal court, your record is removed from the database, so there's no further comparison possible.
The database produces a very high proportion of successful matches.
Our experience with the database is that when a police officer asks for a crime stain to be examined, there's about a 40% chance that will subsequently result in an identification coming back from the database for intelligence purposes. That's an incredibly high percentage compared to any other type of evidence.
An unexpected bonus of the database is that many crimes are solved almost randomly, because the same criminals offend again and again and again.
An example which springs to mind is a person arrested for a disturbance at a petrol pump in West Midlands. His DNA was taken, added to the database, and was found to be a match to an unsolved murder.
Once the database was in full operation, the detectives realised that many unsolved cases could be methodically reviewed using these new techniques, what's called cold case review.
We have cases going back 30 years which we've reinvestigated using DNA technology. It's quite possible that DNA from 30 years ago or more will survive and provide the same information we can get in a modern day case.
Northampton, a small market town in England's East Midlands. 5 times during the 1980s, women were raped in their homes by the same man. The rapist then committed 3 rapes in nearby towns. 14 years after his first rape, he thought he'd got away with all his crimes.
These are the types of premises that Keith Samuels was breaking into. All old Victorian terrace with enclosed rear gardens, and he was able to identify either single women within the premises or premises where girls were alone on the particular occasion when he broke in. He was aware that with these types of properties, very few of them had burglar alarms, and he was able to breach the security of them quite easily.
The victims provided the police with an artist's impression, and clues were found. Small samples of hair, blood and semen, but not enough back then to get a DNA profile.
We can do another search through and see what we can find on
Yeah.
Around 1990, the amount of DNA required was fairly substantial. You need a piece sort of that size, about 1.5 inches across, either semen or blood, to actually get a profile from.
Even though the case seemed hopeless, the Northamptonshire police meticulously filed away all their evidence in their archive vaults, including the clothing with minute traces of blood and semen, for over a decade. until recently and the new DNA database. Suddenly, the Northamptonshire Police had the means to reopen what had been a cold case.
We're going back to 1984, so sort of like, at the time it was 14 years old, but the DNA is fairly long-lived, and the Forensic Science Service had kept those semen samples all that time, and it was still viable enough in one of the 4 offences that we have, that we had to actually give a DNA profile.
Meanwhile, not realising the police now had his DNA, the rapist committed a new, unconnected crime.
We had some luck within this in that Samuels at that time was using an escort agency and had used a young lady from out of the county and had dropped a stolen cheque on her.
Samuels was arrested for this. He became agitated and violent, resisting arrest for a relatively minor offence.
The officer was suspicious of him and was concerned that an individual who was being arrested primarily for a stolen cheque was willing to use violence to resist arrest.
A DNA swab was taken from Samuels, which linked him conclusively to the Northamptonshire rapes. Keith Samuels is now in prison, serving 9 life sentences. In Northamptonshire alone, the DNA database has solved thousands of crimes.
Since 1995 up to the present day, we have got almost 2,000 hits on the database where it has linked particular offenders to particular crime scenes. And if you think that when we interview for one offence, several others may be cleared up at the same time by that offender admitting them, we've probably got possibly up to 10,000 crimes detected in Northamptonshire through DNA in the last 5 years that without these advances in the technology would clearly not have happened.
There are dangers in relying solely on DNA evidence. There are civil liberties implications when large numbers of us have our DNA kept on government-controlled databases, especially if those databases might be vulnerable to mistakes.
If I shake someone's hand, that person's DNA is now on my hand, and if I open a door, I could quite easily leave that person's DNA on that door handle, although they've never even touched it. And DNA is very easily planted now as well. You could, for example, take a cigarette end that you found in a pub or you found on a street corner, and you could take that along to the crime you're going to commit, and you could leave that in the house that you've burgled. And we'd look at that, and our initial reaction would be, that's going to be the offender's DNA on that cigarette end.
The future for forensic science is even more startling than the present.
We see the advent of a handheld DNA reader, where the technology is already there, but the miniaturisation and development needs to be established. But we imagine perhaps a police officer taking a DNA sample at the scene of a crime, interrogating via a satellite link the national database, and obtaining a result instantly.
Add to this even more sophisticated databases. Already, West Midlands Police have a database which combines every kind of forensic evidence.
DNA, fingerprints, footwear, tool marks, drugs, handwriting, those sorts of things.
The computer uses a simple search program to reveal previously undetected patterns in crime.
Instead of concentrating on single cases, what we're learning is that we can concentrate on whole masses of cases at the same time. It keeps its eye on every case you're investigating, not just one. And it's looking for links between isolated cases. I've loaded the name of a known offender in the Birmingham area, and he's connected to quite a number of crimes, and he's also connected by alias to other people. What we've got here is an overview of the links that we have to this particular individual. And as you can see, this individual is a mini crime wave. These lines here around that square indicate evidence type links. There's a DNA. There's in fact a partial DNA. Let's look at the geography and see a national map. Here we have 16 forensic links in Merseyside, in Liverpool, up on in the northwest corner of England. We've then got 3 forensic links in the West Midlands, and then if we go down to London, we've got 1 forensic link. It might be useful to know that there is a main motorway that connects Liverpool with London called the M6. And this individual, we think, was operating as a burglar by stealing cars, coming off the motorway network, committing crime. We did in fact eventually learn that he lived in Liverpool.
The Flint's database will radically increase the number of detected crimes.
We discovered for every 1,000 cases there are an additional 467 links when you apply this approach. You discover 46.7% more links than had you dealt with the information in the old way.
Now that the Human Genome Project has roughly mapped human DNA, it will soon be possible to predict a suspect's physical characteristics from a DNA trace.
We have tests now which can determine whether a person has red hair genetically, so we could interrogate the stain in that way. Obviously, if we have other hair types, skin colour types and physical appearance generally, that would be very useful. So for instance, we're looking at dimples in chins and physical height and facial dimensions and establishing the link between that and a person's DNA profile. It's very early days of the research, but there does appear to be a genetic link that we can define. So we see building up a picture of a person's physical appearance from their DNA profile found at the scene of the crime, and that's a very exciting possibility.
Science can solve crimes, though ultimately it's just a tool of ordinary coppering at routine infringements. But from those mundane incidents, science increases the chance of a successful conviction. Ironically, most forensic evidence never comes to court. The criminal sees the evidence stacking up against him and decides to plead guilty. And then he's on the database for life.